Good morning. All right, so we're going to start with chapter 4 today. This is 4.1 exponential functions. I did just open the content folder for chapter 4 in the course content section of Blackboard. So if you want to follow along in the slides there, those slides are posted now. I'm also going to work on getting the videos for these sections posted. And then that way, if we do skip over any examples, then you'll at least have access to those examples in those videos. Okay. Don't forget that tonight at midnight, test 3, the chapter 3 test will be posted. That will be due midnight on Friday. So you got 2 days to get that done. So find some time either tomorrow or Friday to make sure you've got a couple hours to sit down and take that test. Okay. Any questions, comments, concerns before we get started? Number 7 from the practice test. Yeah, let me find the practice test because I don't have that pulled up right now. Let's see. All right, so number 7 from the practice test. We're basically looking for x and y intercepts and all the asymptotes. Okay, so those are the things I'm going to be looking for on the actual test. So what's the first thing we would want to do with this rational function to be able to find those things? All right, good. Now to find those, though, what's the first step? What do we want to do first? Factor. Good. So let's factor the numerator, factor the denominator, because remember, we need those factors to find the vertical asymptotes. And if any factors cancel, then there's not going to actually be a vertical asymptote there. Right, so I'm going to simplify this. Right, so if we factor the numerator, what can we do in the numerator? Good. We have a common factor of x. I'm going to bring that out. That'll leave us with 2x squared minus 5x and minus 7. Right, now, what about the denominator? What would those factors be? Okay, so we got x minus 2 and x plus 1. Good. Now, once we have that, we need to look at the numerator again, see if we can factor that any further. So that 2x squared minus 5x minus 7, can we factor that into 2 binomials now? Okay, so I know the factors of 2x squared have to be 2x and x, right? Okay, good. So we're going to have 2x and x. We know the factors of 7 are only 7 and 1. In order to get that 5 in the middle, though, I'm going to need the 7 here and the 1 here. I know my signs need to be opposites. I need the bigger value to be a negative to give us the negative 5. So that's going to be a minus 7 and a plus 1 here. All right, now, what do we notice once we get those factors? Yeah, the x plus 1 is a common factor, so it's going to cancel out, right? So I can cancel those out. So then what we're left with really is x times 2x minus 7 over x minus 2. Now, let's go through and see what we can find. Let's start with vertical asymptotes. How would I find the vertical asymptotes this time? Okay, good. Set the denominator equal to 0, and since the only thing left in the denominator is x minus 2, we're just going to have x minus 2 equals 0, and so our vertical asymptote is going to be what? Just x equals 2. Good. And don't forget, it's the equation x equals 2, right? So don't forget the x equals part, because otherwise you won't get full credit for the vertical asymptote if you don't have the entire equation, okay? So x equals 2 is our vertical asymptote. Now, what about horizontal? Okay, good. So we look at the degree in the numerator and denominator first, right? So if we look there, we have a 3 and we have a 2. Well, that means that the numerator's degree is bigger than the denominator's degree. So what does that tell us about horizontal asymptotes? There are none, right? So in any time the numerator's degree is higher than the denominator's degree, we have no horizontal asymptotes. We can just say there are none. Now, what does that mean we're going to check for then? Slant. Good. So we got to find a slant asymptote this time because the numerator's degree is exactly 1 bigger than the denominator. How do we find slant asymptotes? Long division. Good. So I'm going to take what's on the bottom here, put it on the outside. We've got x squared minus x minus 2. And we've got 2x cubed minus 5x squared minus 7x. And I'm just going to put a plus 0 just in case we need that term down there at the end. All right, so I'm just going to go through the long division process, right? We've reviewed this last week. This is 2x cubed over x squared, which is just going to give us a 2x. I'll put that up here. Then we multiply. 2x times x squared is 2x cubed. 2x times negative x should give us a negative 2x squared. And 2x times negative 2 is a negative 4x. Now we're going to subtract all of that. 2x cubes cancel out. Negative 5x squared minus a negative 2x squared becomes addition. So that's negative 3x squared. Negative 7x minus a negative 4x also becomes addition. So that's a negative 3x. And we can bring down the plus 0. Now we look at that first term down here, first term outside. So that's negative 3x squared divided by x squared gives us negative 3. Now we have a minus 3 up here. Again, we distribute. And that gives us negative 3x squared plus 3x and then plus 6. Subtract again. The negative 3x squares cancel out. Negative 3x minus 3x is going to give us a negative 6x. 0 minus 6 is going to be a negative 6. We can't divide anymore because negative 6x we can't divide by x squared. So what we look at now is just the quotient piece of this up here. And so our slant asymptote is y equals 2x minus 3. Any questions about how I got that slant asymptote now? So the x plus 1, so I was looking at this 2x squared minus 5x minus 7 piece, right? And so I had to think about what are the factors of 2x squared? That gave me 2x and x. Then I had to think about the factors of 7. The only factors of 7 are 7 and 1. then it's just a matter of where do I put the 7 and 1 to end up with a negative 5x. So in this case, I need a minus 7 here and a plus 1 so that I get a negative 7x and a plus 2x to give me that negative 5x. Does that make sense? Okay. Yeah, and then once we have that common factor in numerator and denominator, just make sure you cancel that out. So then we remember the vertical asymptote, there's only 1 this time since that x plus 1 does cancel. Yes, so y equals 2x minus 3 is the slant asymptote now. And again, make sure you write it as that equation, y equals 2x minus 3, because it actually is the equation of a line. Any questions about the asymptotes now? Okay, now the other piece is the intercepts, right? So let's look at x-intercepts first. How do we find x-intercepts? Okay, so we set the entire equation equal to 0, right? So we let y equal 0 in this case, so that's going to be 0 equals. Now, for this fraction to be equal to 0, that means the numerator needs to equal 0, right? We don't care about the denominator because we already found the asymptotes for this. So it's just going to be the x times 2x minus 7 has to equal 0 now. And again, we don't need the x plus 1 because that factor canceled out, so we know there's going to be a hole there that cannot be an x-intercept. Now, once we have that, now we can just set each one of those factors equal to 0. So that's going to give us x equals 0 or 2x minus 7 equals 0. So one of our x-intercepts is definitely 0, and then the other one's going to give us what? Good, just move the 7, divide by 2, and so we end up with x equals 7/2. So those are the two x-intercepts. Now, remember, you can also use Desmos to check yourself here, right? So if you graph this in Desmos, you can actually look at where those x-intercepts are, and you should get 0 and 3.5 decimal-wise, right, which is 0 and 7/2. All right, now how do we find y-intercepts? Good. Let x equal 0. The easiest place to do that is probably back in the original. Okay, so if we do that now, that's going to be y equals 2 times 0 cubed minus 5 times 0 squared minus 7 times 0 all over 0 squared minus 0 minus 2. And so if we simplify all of that now, what's that going to give us? Just 0, right? Because the numerator is 0, denominator is going to be -2. 0 over -2 is just 0. So now I have my x-intercepts, have my y-intercepts, have all of my asymptotes, including slant asymptotes. That's what I'm looking for, right? So the describe in behavior piece here, don't really worry about that. What I was really looking for that was that slant asymptote, just to describe what's happening as you go towards infinity and negative infinity, okay? Any questions at all on that one now? And again, if you don't have a horizontal asymptote, then make sure you look for that slant asymptote. All right. So let's jump back to chapter 4 now. All right, so like I said, 4.1, we're going to look at exponential functions now. So these are a new type of function that we haven't considered before, but we have looked at exponents before. But now we're just going to look at, well, what happens if the x happens to be in the exponent of a function? What does that actually look like graphically? And then we'll also get into how do we solve equations that involve those exponents. All right, so the exponential function with a base of a is defined for all real numbers x by this function here. F of x equals a to the x. So a is going to be a number, and then your variable x is going to be your exponent now. Now notice it says that a needs to be greater than 0, okay, because we're always going to consider our base to be a positive value. And then we'll think about putting negatives as being like reflections and things like that in terms of our transformations. And the a value can't be equal to 1, right? Because 1 to any power is going to be 1, and that would just give you a horizontal line at 1. So we need some base other than 1, and it needs to be a positive value. That's what's going to give us an exponential function, okay? All right, so let's take a look at this. We've got f of x equals 3 to the x. That's an example of an exponential function. The base is 3, and our variable x is in the exponent. We just want to evaluate each one of these points now. All right, so if I want to find f of 5, what am I going to have to do to calculate f of 5 now? Good, just raise 3 to the 5th power, right? I'm putting that 5 in place of the x. We have 3 to the 5th. And at that point, we can just go to our calculator, right? So just make sure you know how to put these in the calculator. Right? You have your caret key, the little house top. So if you put in 3 to the 5th power, what's that going to give us? Good, that's going to be 243. Any questions about how to get that value using the calculator now? Okay, now f of negative 2/3. We're going to do the same thing. We're going to take the base of 3 and we're going to raise it to the negative 2/3 power. Now be careful this time. Make sure that the negative 2/3 is in your exponent. So some calculators, you move everything into the exponent so you can easily see that it is. Other calculators won't, and so you need to make sure you put parentheses around the exponent to make sure it's all grouped together. Okay, so if you do 3 to the negative 2/3 now, you're going to get a decimal, right? So let's do 4 decimal places. What would that give us? Good, 0.4807. Anybody not able to get that value there? All right. Now let's look at the next one. Again, our base is 3. This time pi is the exponent. So again, we'll go to 4 decimal places. So what's 3 to the pi power going to give us? All right, so we have 31.544. I think, let's see. I think I had a 3 there when I rounded it. Yeah, so the decimal point after the 2 is an 8, right? That value is an 8, so that would round it up to a 3. And so this should give us 5443. Okay. Questions on that one? In this case, make sure you use your pi key on your calculator. Don't just round that to 3.14, right? Because that could make a pretty significant difference in the decimal value that you get there. Right, and our last one here, we're doing 3 to the square root of 2. And we're just going to raise 3 to the square root of 2. And again, if you have a calculator that doesn't automatically move up to the exponent like that, you're going to need to actually group that in parentheses. So if we do 3 to the square root of 2, again to 4 decimal places, what should we get? Good, 4.7288. Any questions at all about putting those in the calculator to find those values now? So just pay attention, Haley, and WebAssign to how many decimal places they ask for. Generally speaking, if it was on a test for me, 4 is what I usually want. But sometimes, WebAssign might ask for 5 or 6, sometimes even. So just pay attention to what they're asking for. I'll also say that when we start doing some of the real world problems, you might want to even keep more until your final answer, like throughout the problem, just so your final answer is a little more accurate. Any other questions there? All right. So let's take a look here. Now we want to draw the graph of each one of these functions. Okay, so again, we could use Desmos, right? But I want to do this by hand first, just to get an idea of what these actually look like. So if I want to sketch these graphs by hand, what would I need to do first if I don't know what they already look like? Okay, good. So let's make a table of values, right? X and Y values, so that we can plot some points and figure out what this looks like. Now, in general, it's always nice to have some negative values and some positive values. So I'm going to start here with -2, -1, go with 0, 1, and 2, right? So just get those 5 points, see if that gives us enough information to see what this looks like. Okay, so now it's just a matter of substituting those values into our function and see what we get. So if we find f of -2, again, we're taking the -2 now, we're substituting it into our function, so that's going to be 3 to the -2 power. Now, you could do that in the calculator, get a decimal, that's fine, right? I want to do this by hand, though. Whenever you have a negative value, what can we, in your exponent, what can we do with it? Okay, good. Move that to the denominator to make it a positive exponent. So this becomes 1 over 3 squared. So what is 1 over 3 squared going to become? Just 1 over 9. Good. So we have 1/9. That's going to be our value now at -2. Now we're going to go through and do the same thing with all these other points. So I need to find f of -1. That's 3 to the -1. And so what would that give us? Good. So it's going to be 1 over 3 to the first power, so just 1/3. Now we've got a value of 1/3. Let's look at f of 0. So what's 3 to the 0 power going to give us? Good. So anything to the 0 power, always going to be 1, right? So it doesn't matter what that base is. If we raise it to the 0, it's always 1. Now we need f of 1. So that's going to be 3 to the first power, which would be what? Just 3. Good. And then finally, f of 2 is going to be 3 squared, and that will give us what? That's 9. Good. All right, so now let's come over here and see if we can sketch this graph using those points. All right, so I know when x is -2, my value is 1/9. So 1, 2. And so if I put 1 right here, 1/9 is a pretty small fraction, right? We're going to be down here pretty close to 0. I'm going to put a point right up here now. Now, 1/3 at -1, slightly more than 1/9, right? Still not to to +1, but just slightly higher, right? So we're going to have a point right here. My y-intercept now, when x is 0, y is equal to 1. So I'm going to cross my y-axis at 1 right here. Then when I go over to 1, I have a value of 3. 2, 3. I have a point here. And then finally at 2, I'm all the way up at 9. So 4, 5, 6, 7, 8, 9. Here's 2 and 9. Any questions about just plotting those points now? All right, now let's think about here, right? As I go, let's say to the right on my graph now, what's happening to those values as I move to the right? Okay, so they're not even just doubling, right? They're actually being multiplied by 3 every single time, right? So I had a value at 3, then I had a value at 9. The next value is going to be up at 27 because that would be 3 to the third power, right? So I'm actually tripling these values every single time I move to a new x value. So they're growing exponentially now, right? So this is an exponential growth. And so this thing's just going to shoot up towards positive infinity like this now. Now let's think about to the left-hand side. You can see here that we're getting like 1/3, 1/9. If I were to do a -3, that would be 1 over 3 to the third, which would be 1 over 27. What's the smallest value, or I guess, will I ever get a negative value? Let's start there. Can I ever get a negative value out of this function? No, right? Because no matter what negatives I put in there, it's just going to become a fraction, right? And it's still going to be positive. Will I ever get 0 out of this? No, because again, I'm always going to get 1 over something, right? So I'm always going to get a fractional value. These fractions are going to get smaller and smaller and smaller, but I'm never actually going to get 0. And so what ends up happening is we have this horizontal asymptote now at 0. And so our graph looks something like this. Now, in general, when you have a graph that looks like this, we call this a J-shaped curve because it kind of looks like the letter J. So that exponential growth is going to be called a J-shaped curve. Any questions about the graph of 3 to the x now? All right, let's do the same thing for g of x. Right, so we've got 1/3 to the x. I'm actually going to use the exact same values for my x this time. -2, -1, 0, 1, and 2. All right, so if we look at f of -2, it's going to be 1/3 to the -2 power. So how would you do 1/3 to the -2 power? Good. So remember, if you have a negative exponent with a fraction, we're allowed to flip the fraction to make that a positive exponent. So this actually becomes 3 to the +2, which is actually going to give us what then? 9. Good. So our value at -2 is 9. Let's do f of -1. Again, that's going to be 1/3 to the -1. Use that same property, right? We flip the fraction, make that a positive exponent. So this just becomes 3 to the first, which is just what? Just 3. Good. Our value at -1 is going to be 3. Now we can do 0. So we have f of 0. 1/3 to the 0 would give us what? Just 1, right? Anything to the 0 power, always going to be 1. All right, and then if we do our f of 1, that's just 1/3 to the first power, which is 1/3. And then f of 2 is going to be 1/3 squared, which would give us what? So if we square the 1/3, what do we get? So remember, we can square the numerator, square the denominator. There you go, right? So 1 squared is 1, 3 squared is 9, so we get 1/9. That's going to be our value here. Any questions about finding those values? All right, now let's sketch the graph. So if you notice here, we got the exact same values for y, just in the reverse order, right? So we still got 1/9 all the way to 9. They're just flipped now. So when I go over here to -2, at -2, my value is 9. So I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up here. At -1, I have 3. So that's going to be 1, 2, 3 right here. My y-intercept is still 0, 1, right? So that still crosses right here at 1. And then as I go towards the positives, now I get those fractional values. So at 1, it was 1/3. And at 2, it was 1/9. Now the same thing's going to be true again. This time as I go to the left, right, it's growing exponentially to the left, right? So I'm going up towards positive infinity. This graph's going to look something like this on the left-hand side. And then as I go to the right, I still can't get any negative values. I still can't get to 0. I'm just going to keep getting these smaller and smaller fractions. And so this thing is going to approach 0 and give us an asymptote along the x-axis again. Okay. Now, what do you notice about those two graphs? Yeah, it's just a reflection, right? In this case, it's a reflection over the y-axis. And if you remember our transformations, the way we get a reflection over the y-axis is to make the x value negative, right? And so if I were to do that here and say 3 to the -x, remember when you have a negative exponent, we can flip the fraction. So 3/1 becomes 1/3. And so that's why this right here is equivalent to that. And that's why it's just a reflection of the graph that we started with, 3 to the x. Okay? So 3 to the x and 1/3 x, or sorry, 1/3 to the x are actually the same graph because, or a reflection of the original graph because of that negative exponent now. Now, in this case, we call the first one a J-shaped curve. This one down here now is what we call an L-shaped curve, because it looks more like the letter L now. Now, in general, that first graph is going to be used for exponential growth, right? So if we have a situation, a real world problem where we're growing exponentially, then it's going to give us that first graph, that J shape. If we have a situation that's decaying exponentially, then we're going to have this other graph, and it's going to be more of an L-shaped graph. And we'll look at both of those situations later in the unit. Any questions on the graphs now? All right. So here's just kind of a synopsis of what we just looked at. Okay, so this first one here, no, actually, I'm going to change that due date. So I want to kind of see how far we get today, and then I can kind of adjust that due date accordingly. But yeah, that's not going to be due. All you need to worry about for this week is the test that's due on Friday. Okay. Good question, though. All right. So if we look here, right, we have that J-shaped curve. That's the first graph here. We have the L-shaped curve. That's the second graph. Anytime your A value is bigger than 1, right, that 3 to the x that we had an A value bigger than 1, that's going to give us that J-shaped curve. Anytime we have a fractional value between 0 and 1, that's when we're going to get the L-shaped curve instead, right? So bigger than 1 is exponential growth, and then anything between 0 and 1 is going to give us exponential decay instead. And again, in both cases, our domain is all real numbers. And the range, we're going to have that horizontal asymptote at 0. And it's going to be everything above that. So from 0 to infinity, it's going to be the range of those graphs. And again, notice here, in both cases, the y-intercept is at 1, because anything to the 0 power is going to give us 1. So only if we have other types of transformations is that ever going to change, right? If you did a shift or something, then you could have a different y-intercept. Now, this time we want to actually find the function. So they give us the graphs. We want to figure out what that function would have to be. All right, so based off of what's given here, what do you think we might be able to do to help us find that function? Okay, all right, so good. You're on the right track, right? So let's think about what we've got here. We've got an x value and we've got a y value, right? And we're trying to get this form of our function. So what we can actually do now is substitute the x and the y in place of x and f of x, and we need to solve for the base. We need to find that a value. So for this one, that's going to be 25 equals a to the second power. So what are we actually going to want to do this time if we want to get the a value? Take the square root of both sides. Good. So if I take the square root here and the square root here, it's going to give us a equals what? 5. We don't need a plus or a minus here, right? Because we know that this is going to be a positive value for our a in terms of what an exponential function is going to look like. And so now we can just say that f of x is equal to 5 to the x power. So if you're given a graph with a point, right, and we know we're looking for a to the x, plugging your x and y, solve for a, that gives us our base. And now we know that that function just has to be 5 to the x power. Any questions on that one? All right, can do the same thing with this next one. So again, we have 3 as our x value, 1/8 as our y value. We plug those in. We have 1/8 equals a to the 3rd power. So what are we going to have to do this time? Good. This time we need a cubed root. So if we take the cubed root of 1/8, what would that give us? So remember, we can take the cube root of the numerator, take the cube root of the denominator. What's the cube root of 1? That's just 1. What's the cube root of 8? It's going to give us 2, right? Because 2 to the 3rd power will be 8. So this time our a value is going to be 1/2, 1/2. And so our function is just going to be 1/2 to the x. And again, if you look at your graph, that makes sense, right? We have an L-shaped curve this time. That means our a value needs to be between 0 and 1. We got a fraction of 1/2, which is between 0 and 1 now. Any questions on that one? All right. So now let's look at some transformations. Okay, so we're going to use the graph of 2 to the x to actually think about these different types of transformations. So first off, if I were to sketch the graph of y equals 2 to the x, what shaped graph is that going to be? It's a J, right? So we know it's exponential growth because the a value is bigger than 1. We know the y-intercept is going to be 1 because that's true of all of these, right? Anything to the 0 power is 1. So we're going to have our y-intercept here. We're going to have our asymptote at 0, J-shaped curve. So it's going to look very similar to 3 to the x. It's just not going to grow quite as fast as 3 to the x does, right? But it's still going to be a J-shaped curve. Okay, so now let's think about our transformations that we can apply to that. So if we look at g of x now, what type of transformation are we going to have? Good, right? So we're adding 1 to the 2 to the x. That's going to shift up 1 unit. We have a vertical shift up 1 unit. So now let's think about what that graph's going to look like. So what's going to change then about that original graph if we shift everything up 1 unit? Okay, good. The horizontal asymptote now, instead of being at 0, gets shifted up 1 unit. So now we're actually going to have an asymptote at y equals 1 instead. Okay, so there's that. What else is going to change? Good. The y-intercept also gets shifted up 1 unit. So now it's going to be up here at 2 instead. So it's still a J-shaped curve, still exponential growth. But if we shift everything up 1 unit, the asymptote gets shifted up 1, and that y-intercept gets shifted up 1. And so now we know the horizontal asymptote is going to be y equals 1 instead, right? And that was one of the things they asked us to find here. The other 2 things are domain and range, right? So let's think about domain. What's the domain for this new function? Good. It's still all real numbers, negative infinity to positive infinity, right? I can still put any x value I want in there. What about the range? Good. Since we have that horizontal asymptote at 1 now, everything was shifted up 1. Now it's going from 1 to infinity. And again, we don't want to include the 1 because 1 is an asymptote. Any questions on domain and range for that graph? All right, so look at h of x. So now we've got negative 2 to the x power. What type of transformation is that going to give us? Good. So it's a reflection over the x. Remember, if you put a negative out front of a function, right, that's always going to give you a reflection over the x-axis. So now go back to your parent function, right? If we reflect over the x-axis, what's going to change? So just take this original parent function over here and think about if we take that entire graph now and reflect it over the x, what would happen? Okay, good. So it's going to be an upside down j, right? Where would the y-intercept be? At -1. Good. So that point at +1 gets reflected down here to -1. Where's our asymptote going to be? Still 0, right? It's just approaching from the bottom instead of the top this time. And so it's going to look like this. Okay, so again, we still have that horizontal asymptote at y equals 0. And now our y-intercept becomes -1 instead of +1 because we reflected that j over the x-axis now. Any questions about the graph? All right. Domain and range. Why wouldn't it flip every odd exponent? Because the negative is not with the 2, right? The negative is out front. So it's still 2 to the x, and you're making the entire thing negative. If the negative was grouped with the 2, if it was parentheses -2 raised to the x power, then that's why we have to have a positive base, right? Because yes, that would affect whether it's positive or negative every time you hit an odd exponent. Okay? So all of our exponential functions will have a positive base, and then the negative out front is not part of the base. That just gives us a reflection now. Does that answer your question? Okay. All right. So now domain. What's our domain this time? Okay, good. All real numbers again. Nothing changes there. And the range this time is going to be what? Okay. So remember, though, the smaller value needs to come first. So just make sure you start with negative infinity and then to 0, right? Any questions on that one? Okay. So, like I said, I'm going to get the videos posted. So if you want to see that last part, right, then you can actually look at what that is. We'll pick up with the next example when we start on tomorrow. Yeah, I had to think about what day it was. So yeah, so tomorrow I'll adjust the homework due date. Okay, but again, the main thing you need to worry about this week is the test will be posted tonight at midnight. Make sure you get that done by Friday at midnight. Okay, so that's the only thing you need to worry about this week. And the next homework will be due sometime next week once we get through these first few sections. Okay. Have a great afternoon, and I will see you all tomorrow.